Hello everyone, myself Dr. Seema from Alobasics. Today we'll discuss AC circuits, which is 13th chapter from Maharashtra State Board Physics syllabus. Last topics of AC circuit chapter, that is sharpness of resonance, Q factor, and choke coil. Today let us discuss this. Sharpness of resonance, Q factor. Earlier, we have studied series LCR circuit and parallel LC circuit. Both these circuits are capable of producing oscillations, or we say that producing resonance, and due to that we call them as resonant circuits. Now today we have to study sharpness of resonance for series resonant circuit, and already we have studied series resonant circuit in electrical resonance part of this chapter in our earlier lecture. In that we have seen that at resonant frequency omega r, that circuit is said to be resonant circuit. What is this resonant frequency? Which frequency we call as a resonant frequency? Actually, when we talk about resonant frequency, we consider it as FR, but here it is angular resonant frequency, which is given by omega r. And we say that at omega r, inductive reactance is equal to capacitive reactance. Now, as inductive reactance is equal to capacitive reactance, here we write inductive reactance is given by omega RL for the particular value of angular frequency omega r. I'm writing this is equal to 1 upon omega RC. This gives me capacitive reactance at omega r. Now, if we simplify this equation, we write that omega r is equal to 1 upon under root LC. Or as omega r is equal to 2 pi fr, fr is equal to 1 upon 2 pi under root LC. All these things we have discussed in detail in electrical resonance, in that series resonance. So we are familiar with that. And here one more thing, just we revise which we have studied earlier, that series resonance circuit acts as a pure resistive circuit. So for that I0 is given by E0 upon R. As XL is equal to XC, impedance is given by R. When I consider for value of omega other than omega R, for omega R I say that XL is equal to XR. That is okay. But is it possible for all values of omega? No. Then the values of omega other than omega R, amplitude of current is less than I0. Current's amplitude goes on decreasing. Its value is smaller than that of I0 for all other values of omega. We have studied graph of this also in series resonance circuit. This is the graph between current and the frequency. Here I am taking angular frequency. See, variation will be same for frequency or angular frequency. Already we have seen this nature of graph earlier also. Now few more details we have to study here regarding that. And in this graph we have three graphs, and these three graphs are for different values of resistors. R value is changing here, and you can see here this is for R1, R2 and R3, where R1 is less than R2 is less than R3. As current is maximum for R1, then R2 and then R3. And this is quite natural. As value of R goes on increasing, value of I0 goes on decreasing. Here we know that there is inverse relation. So this is quite possible. Now when we are studying with this, particularly I'm having nature of this graph, it's such that as frequency goes on increasing, initially current I0 is increasing. It is attaining certain high maximum value, and again if we increase frequency, value of I0 goes on decreasing.
It is represented here. Now in this graph, marking a perpendicular line to x-axis which is passing through the maximum value of I0. So I'm making two parts of this graph. One is on the left side of the maximum value and another one is on the right side of the maximum value. Now what this left side indicates? Left side indicates that inductive reactance XL is less than capacitive reactance current for series resonant circuit. See, this omega R is giving me maximum current. For all other values of omega on left side as well as on the right side are less than that of I0. Now here I'm choosing value of I which is I0 by root 2. I0 by root 2 means what? I'm taking IRMS value. At this I0 by root 2 value, I'll draw a perpendicular on y-axis, and this perpendicular cuts this graph in 2 points, one on the left side of the maximum I0 and second on the right side of the maximum I0. This indicates that there are two values of omega for which current is I0 by root 2. Value of omega for which value of amplitude of current is I0 by root 2, then power dissipated by the circuit becomes half. Now why I have chosen this particular value of current? Because at this value of current, power dissipated in the circuit becomes half of the maximum value. As it becomes half of the maximum value, this frequency is known as half power frequency. Now, which is this frequency, half power frequency? This one is half power frequency and this one is half power frequency. There are two half power frequencies and we call them as omega 1 and omega 2. So here I say that this is omega 1 and this is omega 2. See, because of the short of space, I'm not able to write down here omega 1 and omega 2. Directly I have written their values. The difference between this omega 2 and omega 1 is considered to be bandwidth. Before going to bandwidth, first of all, I'll consider value of omega 1 and omega 2. So omega 1 is given by omega r minus delta omega. And omega 2 is given by omega r plus delta omega. Now what is delta omega? Delta omega is this much. This is delta omega as well as this is also delta omega. We can write values of omega 1 and omega 2 as omega 1 is omega r minus delta omega and omega 2 is equal to omega r plus delta omega. One is less than omega r, one is greater than omega r. So one is on the left side of omega r and one is on the right side of the omega r. Now from this, I want to find out bandwidth, and bandwidth is the separation between omega 2 minus omega 1. So this minus this, it is equal to 2 delta omega, because this is delta omega, this is delta omega. So delta omega plus delta omega will give me 2 delta omega. This represents bandwidth of this curve. Bandwidth of the curve is taken where we are taking these frequencies at I0 upon root 2. That you have to keep in mind. Now on that basis we have to define this Q factor. Now what is Q factor, or that is also known as quality factor? Now what is this Q factor? Q factor is the sharpness of resonance defined as a ratio of resonant frequency to bandwidth. Now what is sharpness of resonance? See here, it has a peak value. Now here also there is a peak. Here also there is a peak. But what is difference between these three? This is little bit flattened as compared to this. This is more flattened as compared to these two. क्या हुआ है? यहाँ पे sharp peak आ रहा है, यहाँ पे flat हुआ है, यहाँ पे फिर से flat हुआ है. तो ये क्या बताता है मुझे? ये बताता है कि यहाँ पे sharpness ज्यादा है, यहाँ पे sharpness कम है, यहाँ पे उससे भी कम है तो ये मुझे क्या बताता है, यहाँ से यहाँ तक रेडियस रेजिस्टर क्या हुआ है, बढ़ते गया है, बिकॉज R1 इज द लोएस्ट हैविंग वैल्यू एंड R3 इज मैक्सिमम अमंग दीज थ्री। तो यहाँ पे रेजिस्टेंस कम है, रेजिस्टेंस कम है तो शार्पनेस ज्यादा है, रेजिस्टेंस ज्यादा है तो शार्पनेस कम है। अब मैंने ये तो बता दिया, लेकिन ये किस ग्राउंड पे मैं बता रही हूँ, ये मैं बैंडविड्थ के ग्राउंड पे बता सकती। कैसे? क्योंकि मुझे एक बात पता है, जैसे जैसे रेजिस्टेंस बढ़ेगा वैसे वैसे I0 की वैल्यू कम होगी, जैसे जैसे I0 की वैल्यू कम होते जाएगी वैसे वैसे I0/√2 की भी वैल्यू कम होगी, और ये वैल्यू जैसे जैसे कम होने वाली है वैसे वैसे ये स्पेसिंग बढ़ने वाला है। अगर ये स्पेसिंग बढ़ता है इसका मतलब क्या हुआ, बैंडविड्थ इज गोइंग टू बी चेंज, एंड एज बैंडविड्थ चेंजेस sharpness changes. Now see here, when I'm observing here, bandwidth is given by this. If for this I0, if I'll take somewhere I0/√2, it will be somewhere here, and naturally for this bandwidth will be larger as compared to this one. As Q factor is given by ratio of resonant frequency. Which is resonant frequency? Now here I am talking in terms of angular resonant frequency initially, then we'll go for resonant frequency. So what is angular resonant frequency? That is omega r. What is bandwidth now? Bandwidth is 2 delta omega. So I can write Q is equal to omega r upon 2 delta omega. Now this equation indicates that as sharpness increases, bandwidth decreases. जैसे अगर मैं चाहूँ ये और ऊपर 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 जाने वाला है तो क्या होगा, बैंडविड्थ डिक्रीज होती जाएगी, शार्पनेस इंक्रीज होगा लेकिन बैंडविड्थ डिक्रीज होगी। अगर ये नीचे जा रहा है तो क्या होगा, शार्पनेस डिक्रीज होगा और बैंडविड्थ इंक्रीज होगा। तो हम दोनों चीजें एक साथ नहीं अटेंड कर सकते हैं, इधर वी गेट bandwidth or we get sharpness. Now as I have written this in terms of angular frequency, same thing I can write in terms of frequency, that Q is given by FR, that is resonant frequency, divided by bandwidth. Bandwidth is 2 delta F. See here, if I write 2 pi F, here also I'll write down 2 pi FR, and here also I'll write down delta 2 pi FR. 2 pi will get cancelled. So we can write either this equation in terms of angular frequency, or we can write it in terms of frequency also. This equation tells us about the sharpness of the resonance which we are observing. Now this quantity is dimensionless quantity, as it is ratio of same physical quantities. It is ratio of frequency only. So it is dimensionless quantity. Earlier we have discussed, as the large is the value of Q factor, smaller is the bandwidth. Now this Q factor is again given by one more formula or two more formulae, I say, depending on the circuit. That is given by Q is equal to VL upon VR, or VC upon VR, or EL upon ER is equal to EC upon ER, because in AC circuits, instead of voltage, we are discussing everything in terms of EMF. So you can write it in terms of E also. So this is about sharpness of resonance or Q factor. Now last topic, that is choke coil. In general, in any circuit, we are using resistance. Now what is use of resistance? Use of resistance is to reduce current in the circuit. When we are using that resistance in the circuit, we know that as the current increases in the circuit, heating effect is observed, which is associated with that resistance. And due to this heating effect, there is energy loss. To reduce this energy loss, inductor can be used. So what I say that resistance can be replaced by inductor. Because of this, whenever at our home we are using tube lights, those tube lights are consisting of inductor. In my very first lecture on AC circuit, I told you about choke. The same choke coil here we are discussing. तो जब हम घर में ट्यूब लाइट्स यूज करते हैं तो वो ट्यूब लाइट्स में चोक यूज किया जाता है. What is job of that choke? To reduce current flowing through that tube light. Now what is this choke coil? A choke coil is an inductor with higher value of L. कोई भी इंडक्टर हम यूज कर रहे हैं क्या? नहीं, ये ऐसा इंडक्टर है कि जिसकी वैल्यू ज्यादा है. क्यों ज्यादा है? Because inductive reactance is given by omega L, and as inductive reactance is given by omega L, as the value of L is larger, its inductance is also reactance is also larger, means opposition to current is also larger, and for that purpose choke coil is having higher value of L, and it is used to reduce AC passing through a circuit without much loss of energy. If I use resistor, then there is energy loss. To avoid that energy loss, we are using inductor. This choke, whatever we are using, that choke is made up of thick insulated copper wire wound closely in number of turns over a soft laminated iron core. What is laminated iron core? Why to use soft iron core? All these things we have discussed in electromagnetic induction chapter. So there is no need of discussing all these things again and again. Now here, for us, what is important? Now what is inductor? Inductor is wire wounded closely with large number of turns over a soft laminated iron core. That you have to just keep in mind. But inductive reactance is large for AC of high frequency. It reduces current in the circuit. For higher frequency values, it reduces current in the circuit. But when we have studied inductor, we have studied AD current losses also. These AD current losses which are there for the inductor, they can be reduced by using laminated iron core. Power for this choke coil is given by average power is equal to ERMS IRMS into cos phi. Now what is cos phi? R upon R square plus omega L square. Now see here, I don't have term of C. I don't have omega C or 1 upon omega C, because what I am considering in this circuit only inductor is present with resistor. That is my assumption. There is no capacitor, or in short I say that this is LR circuit. If I have RC circuit, what change will there? Here I'll have R square plus 1 upon omega C square. Right? So for this choke, we can write cos phi is equal to R upon under root R square plus omega L square. As L is very large, this value of L is very large, and R is small. This is small and this is large. What will happen? Cos phi will be nearly 0. This value has a small value. Now as R is small, R square is smaller, and with comparison with omega L square, it is negligible, but it is present in denominator, whereas R has a small value which present in numerator, and due to that the total value of cos phi becomes negligible, or it is nearly equal to 0. And we have seen earlier that if cos phi is equal to 0, power loss is negligible. We call it as a power factor. So if as this value is very small, power loss is also said to be negligible, and the only loss of energy is due to hysteresis loss in ion. See here, in inductor we have eddy current losses, we have hysteresis losses. Eddy current losses we can reduce by using laminated ion core, and hysteresis losses we can reduce by using soft ion core. So from this, in choke coil, what is required? Soft ion core is required to reduce hysteresis losses, and laminated ion core is required for reducing eddy current losses. So what we say that there must be a laminated soft ion core on which large number of windings are present, and that sort of choke we can use for the home appliances, and we can reduce alternating current in the circuit with minimum power loss. So here we have completed theoretical part regarding AC circuits.
This is last theory lecture of AC circuit. Here are questions on today's topics, and today we have discussed two things. One is sharpness of resonance and second thing is choke coil. In our next video, we'll see numericals on AC circuit.
Before concluding this today's lecture, let us discuss on the formulae which we come across this chapter. So next time you will be prepared with all those formulae for solving numericals. Let us discuss in brief the formulae which we come across in this chapter of AC circuits. First formula is E is equal to E0 sin omega t, or E is equal to E0 cos omega t, which represents AC signal. For that, current is given by I is equal to I0 sin omega t plus alpha, or I is equal to I0 cos omega t plus alpha. Here even we can write plus minus. Here also we can write plus minus depending on whether current is leading or current is lagging. If E is equal to E0 cos omega t, we can write it even in terms of sign as E0 sin omega t plus pi by 2. Now what is peak value? Peak value is given by E0 and I0. Average value, E average is given by 0.637 E0 and I average is given by 0.637 I0. RMS value is given by ERMS is equal to E0 by root 2, that is 0.707 E0. Similarly, IRMS is given by I0 by root 2, that is 0.707 I0. E is equal to E0 sin omega t plus minus alpha 1, and I is equal to I0 sin omega t plus minus alpha 1, where alpha 1 and alpha 2 are the phases, or we say that is giving me phase difference. So if I consider that omega t is along x-axis, alpha 1 is the angle between the line and the x-axis. It may be on the positive side or may be on the negative side depending on whether sign is positive or sign is negative. Phase difference phi is given by, for this particular equation, the phase difference phi is given by alpha 1 minus plus alpha 2. It may be positive, it may be negative. It is decided by the situation. omega is 2 pi f, or we can write omega is equal to 2 pi by t. These are the simple formulae. Actually, you are very much familiar of this. Majority times you have used it, but again in this chapter we require it, so just we are brushing it up. Again, commonly used formula, that is T is equal to 1 upon F. Now when E is equal to E0 sin omega t, then for resistive circuit I is equal to I0 sin omega t. There is no phase difference. Then for I0 is given by E0 upon R, and IRMS is given by ERMS upon R. Now for inductive circuit, I is equal to I0 sin omega t minus pi by 2, because current is lagging EMF, and here I0 is given by E0 upon omega L, or which we can write as E0 upon XL, where XL is given by omega L. Now for capacitive circuit, I is given by I0 sin omega t plus pi by 2, because current is leading the EMF, and here I0 is given by E0 upon 1 upon omega c, or it is said to be E0 upon XC, where XC is 1 upon omega c. For series LCR circuit, I is given by I0 sin omega t plus minus phi, where phi is phase difference, and I0 is given by E0 upon Z, where value of Z is given by under root R square plus XL minus XC whole square. Now the next term which we have to discuss, that is tan phi, and this tan phi is given by XL minus XC upon R. For what purpose we use this? It gives me the direction phi. In terms of phi, we can find out its direction. So it is given by XL minus XC upon R. This we came across from the impedance triangle. Next formula in this chapter, which is related to power in AC circuit. First of all, we'll take resistive circuit, and for resistive circuit, power is given by P average is equal to P apparent, because we call it as apparent power, and that is ERMS into IRMS, that is given by E0 by root 2 and I0 by root 2. For inductive circuit, average power is 0. Already we have seen this also. For capacitive reactance, average power is again 0. For series LCR circuit, average power is said to be true power and is given by ERMS into IRMS into cos phi. Same thing we can write as E0 upon root 2 into I0 upon root 2 into cos phi. Now power factor, which is given by cos phi, and that is again given by ratio of true power divided by apparent power, or we call it as it is a ratio of resistor divided by impedance, or resistor and impedance. Now we come to LC oscillation part, in which we dealt with electrical energy UE, or energy stored in capacitor, and this is the maximum electrical energy, which is given by half of Q max square divided by 2, which we can write as half of CV max square also. Now here we are taking this as a maximum charge, because energy also we are considering maximum. But if it is not maximum energy, in that case we can write this UE as half of instantaneous charge square divided by value of capacitor. With the help of that, we can find out this. As we have discussed electrical energy, we have to discuss magnetic energy also, and magnetic energy, or the maximum magnetic energy, is given by half of L I max square. It is not maximum. If it is instantaneous, I say that it is half of L I square only, where I is the instantaneous value. Next equation or next formula which we are discussing, that is I max is equal to under root C by L V max. This is also formula which is applicable for LC oscillations or parallel LC circuit. Now for resonance, we have seen that XL is equal to XC. This is the condition for resonance. There is one more condition for resonance, that is omega RL is equal to 1 upon omega RC. Even this we can write in terms of frequency also. There is no need to again write it. You can do that. Then resonant frequency FR is given by 1 upon 2 pi under root LC. This also we have discussed earlier. Then comes Q factor. This Q factor is ratio of omega R to omega 2 minus omega 1, or ratio of resonant frequency to bandwidth, that is omega R divided by 2 delta omega, which we call as it is resonant angular frequency divided by 2 delta omega. Same Q factor we can write as ratio of resonant frequency to bandwidth. Here I am having angular frequency, here I am having frequency, which we can write as FR divided by 2 delta F also. Just whether I am writing in words or I am writing in symbols, that is the matter. Again, one more formula for Q we have seen, that is in terms of VR upon VL or VR upon VC. That I'm not writing here, but if you want to solve numericals related to that, you can add that in your list also. So here we have completed all the majority required formulae in this chapter. You copy all these formulae in your notebook and be prepared for the lecture of numericals. If you have gone through this formulae, if you are prepared with the formulae, you can solve numericals very easily. So today we stop here. Thank you for watching. See you soon in the next video of AC Circuits.